Hello class, today we're going to go over section 2.8 notes, graphing linear inequalities in two variables. We're going to first start by looking at an example in which we have to figure out whether an ordered pair is a solution of an inequality. So in this first example, they gave us four options for ordered pairs. To check to see if they're a solution, we'll plug them in one at a time for x and y. I'll start with part A, 0 and -3. Recall that the first values are x value, the second values are y value in an ordered pair. So in our inequality, 5x minus 2y is less than or equal to 6. I'll replace x with 0 and y with -3. 5 times 0 is 0. -2 times -3 is 6, so it's a plus 6. Less than or equal to 6. 0 plus 6 is 6, so I get 6 is less than or equal to 6. This is a true statement since they are equal, which means that A is a solution to our inequality. Now keep in mind, you could have more than one solution to an inequality. So if you wanted to, you could check the rest of them to make sure that they don't also work. So if we were to do that, we would take 5 times 5 minus 2 times 5 and see if that's less than or equal to 6 for part B. We get 10 minus 10 is less than or equal to 6. 10 minus 10 is 0. 0 is less than or equal to 6. This is a true statement. For part C, we would substitute 1 for x and -2 for y. 5 times 1 is 5. -2 times -2 is 4. So I get 5 plus 4 less than or equal to 6. 9 is not less than or equal to 6, so C is not a solution. And we could do the same thing for part D. 5 times 3 minus 2 times 3 and see if that's less than or equal to 6. 15 minus 6 less than or equal to 6. 9 again is not less than or equal to 6. So D is also not a solution. Now we'll move on to looking at how to graph these linear inequalities. To graph, you would first figure out if you're going to use a dashed or a solid line for your equation. Note, if it's just less than or greater than with no line underneath your inequality, it would be dashed. If it says or equal to, so less than or equal to or greater than or equal to, that's when you use a solid line to graph. We also have to shade for these when we graph them. So to figure out which side of your line you're going to shade on, you'll pick a test point that's not on the line you just drew. You're going to plug it in to see if it's a solution to an inequality. If it is a solution, then you shade on that side of the line. If it's not a solution, shade on the other side of the line. So in example 2, we're graphing x is less than or equal to 5. Notice it's less than or equal to, so that means it's going to be a solid line. And you're going to want to think of how you would graph it x equals 5. So for x equals 5, we go to 5 on the x-axis. And we would draw a vertical line. Notice it's solid because it's less than or equal to. Now to figure out which side we're going to shade on, we pick a test point. I usually use 0, 0, as long as it's not on the line I draw. So if I use 0, 0 to test, in my inequality, x is less than or equal to 5, I will replace x with 0. 0 is in fact less than or equal to 5. What that tells me is the side that has my test point, since it worked, I will shade on that side. And we're done with that example. Now for the next example, we're graphing 3x minus 4y is greater than 12. Since it's only greater than and not equal to, this will be a dashed line. We can do this by finding intercepts. 3x equal to 12 will give us our x-intercept. Divide by 3. So my x-intercept is 4, 0. For my y-intercept, that's when I make the x 0, so I get -4y is greater than or equal to 12. Divide by the -4. So y is equal to -3, so my y-intercept is 0, -3. I'm going to plot these points. And then I'll connect them using a dashed line, since this is an inequality. For this one, we also have to do another test point. I'm going to use 0, 0 again since it's not on our line. When I test 0, 0, I'll replace x and y with both of them with 0 in my original problem. So 3 times 0 minus 4 times 0 is greater than 12, and I need to see if that's a true statement. Well, 3 times 0 and 4 times 0 both equal 0, so I get 0 is greater than 12. This is not true. Since it's not true, that point is not a solution, which means we need to shade on the opposite side of the line. So I'm going to shade on the bottom portion. And the shading means every point in that line, or in that shaded region, is a solution to your inequality. And that's it for that one. Okay, example 4. You have 2 part-time summer jobs, one that pays $9 an hour and another that pays $12 an hour. You'd like to earn at least $240 a week. Write an inequality describing the possible amounts of time you can schedule at both jobs. Then graph the inequality. So you make $9 an hour at your first job. So 9 times, let's say, X hours for your first job. $12 times Y hours for your second job. Those wages added together, you want to make at least $240 a week. So adding these together, you want to make a minimum of $240 a week. What that means is, if you show this as an inequality, the $9 per hour plus the $12 per hour, you want to be greater than or equal to $240. This is our inequality. Now they want us to graph it. So to graph it, we could find intercepts. To find the intercepts, that's where you make x0 to solve for y, y0 to solve for x. So for my x-intercept, I get 9x is equal to 240 divided by 9. And 240 divided by 9 is about 26 2/3. To find our y-intercept, we make x0. So 12y equals 240 divided by 12. Y is equal to 20. So these are both of our intercepts. Keep in mind this is going to be a solid line because it's greater than or equal to. Let's go by, let's see, can we go by 2s? 2, 4, 6, 8, 10, 12, 14, 16, 18. We can't. So let's go by 3s for the x-axis. And then along the y-axis, we could go by 2s. So when I plot these, I'll have a dot at 0, 20, another one at 26 2/3, comma 0. This is a solid line between the two. And then we have to figure out where to shade. Let's go ahead and use that test point 0, 0. So 9 times 0 plus 12 times 0, and we're going to see if that's greater than or equal to $240. We get 0 is greater than or equal to 240, which is not true. So what that means, we're going to shade on the opposite side. And we're done. In example 5, which is our last example, we have an absolute value inequality that we're going to graph. So for this problem, we have y is less than or equal to negative absolute value of x plus 2 minus 1. This is a v-shaped graph where our vertex is at -2, -1, and our pattern, because of that negative sign in front, is a -1. Since it's a less than or equal to sign, this is going to be solid. So let's start by graphing that V. We start at -2, -1. We're going to go upside down. So we go right 1 and left 1 and then down 1. So your line should look like that. Now, since it's an inequality, we do have to pick a test point to see where we shade. I'm going to use 0, 0 again since it's not on my line. Keep in mind 0, 0 is not the only point you could use. You could use any point that's not on the line you draw. I just find 0, 0 to be the easiest. So when I plug it into that original inequality, I get 0 is less than or equal to negative absolute value of 0 plus 2 minus 1. 0 is less than or equal to negative absolute value of 2 minus 1. 0 is less than or equal to absolute value of 2 is 2, but we have that negative sign in front, so it's a -2 minus 1. So I get 0 is less than or equal to -3. This is not a true statement. 0 is not smaller than -3. Which means instead of shading on the outside of our absolute value graph, we are going to be shading on the inside. Once you're done shading, you are done with this problem. And that's it for notes today. If you have any questions, contact your teacher.